Germany still dominates this industrial jewel to this day. For nearly a century, it has ranked in the world's top 3. With 9 1-ton axles, it lifts 35.7 tons, using a 16.3-meter, 3-section boom. What allows Liebherr, a world jewel, to remain at the pinnacle of the global industry. The Liebherr LTM 1750 costs approximately €4 million. With its telescopic boom, it can reach a height of 52 meters and has a maximum lifting capacity of 800 tons. Even at a maximum operating radius of 160 meters, it can still lift a 1.8-ton load. The first step in production is to use a tap to coat internal threads around the platform. The slewing ring, consisting of a power unit and counterweight, is connected to the crane carrier, allowing the crane and its superstructure to rotate 360 degrees during operation. To reinforce this critical area, Liebherr uses 300 BTS ultra-high-strength bolts. A slewing ring is as simple as a bearing, but it consists of inner and outer structures. The inner ring is typically bolted down directly, while the outer ring is fastened to the crane frame. The 1750 model is equipped with a cab, an engine, and hydraulic supports, which together ensure the continuous operation of the machine. Inside the hydraulic support is a component called a hydraulic accumulator, where 35 bar of nitrogen is used to isolate the hydraulic fluid. If the crane travels over uneven terrain, hydraulic fluid is forced out of the shock absorbers and pushed through the pipes into the hydraulic accumulators, where it absorbs the impact of the bumps with the help of compressed nitrogen. Engineer Mark needs to install 18 of these cylinders, one on each side of the 9 axle groups. Although the 1750 has an exceptional length that exceeds that of a standard heavy-duty truck, its non-driven axles are remarkably light, weighing only 1 ton. Additionally, each of the 4 driven axles weighs just 1.5 tons. The axles are connected by tie rods on both sides. Both the axles and the steering system utilize hydraulic assistance, so purely mechanical systems are unnecessary. See those hydraulic cylinders on either side. Those are the hydraulic assist units. The other 4 utilize an electro-hydraulic conversion via a hydraulic system. 2 independent 1750 systems also enable rear-wheel steering. This design, which differs from direct front-wheel steering, significantly enhances its urban maneuverability. Furthermore, the manufacturer has implemented a dual braking system. For instance, the 6th axle group is equipped with an eddy current brake, which provides auxiliary braking to minimize wear. After the axle is installed, the engineers still need a way to flip it over. That's why they've set up this yellow circular frame that looks like a portal. Once the pivot pin and locking pin are secured, the motor will automatically rotate the chassis forward. The yellow frame weighs about 3.9 tons, but the moment it lifts, the load instantly jumps to 23.3 tons. In fact, the more counterweights a crane has, the greater its lifting capacity. Especially when a crane's net weight exceeds 100 tons, it inevitably requires a more powerful engine. The V8 diesel engine, manufactured in-house by Liebherr, produces 680 horsepower. Furthermore, the transmission and the hydraulic pump mounted above it are all installed during this stage. Maximilian Schitz is the senior engineer here, and he has the final say on the engine's placement and movement. Once it is lowered into position, he takes out his long ruler and walks to the front of the crane to check the clearance on both sides. Since Liebherr did not leave much room in the original design, this means the gap on either side is limited to just 1 centimeter. The 9 axles are all connected via a transfer case, so attaching the drive shaft to the gearbox becomes a bit complicated. You even need someone to crawl underneath and nudge the drive shaft, since you can't align it properly just by working from above. As a crane, almost all of its components have undergone significant modifications. For example, Liebherr even laid this originally upright radiator flat. In addition to cooling the engine, it also cools the air conditioning system and the charge air. The excess oxygen generated further improves the combustion efficiency of the engine and fuel. Meanwhile, a 600-liter diesel tank and a 300-liter hydraulic tank have also been installed. The intricate network of pipes connects at least 5 oil ports, yet it is still missing a crucial cab. It measures about 3 meters in width and weighs as much as a small car. As for this crane beam, which doesn't look particularly sturdy, it is fitted with a bridge girder designed specifically for cranes. You can see that the front end is significantly lower than the chassis. To ensure a smooth operation, engineers also add shock absorbers to both sides. Shock absorbers on mining vehicles have a high failure rate, unlike those used on asphalt roads, which rarely have such issues. Now, a large number of cables need to be routed through the cab chassis to power the electronic switches for the instruments. What looks like a casual second is actually the result of 3 hours of hard work. Only after those 3 hours of effort could they finally move the exhaust pipe into place. The diesel and hydraulic oil are now fully topped up. Only diesel exhaust fluid is missing, an aqueous urea solution used to reduce nitrogen emissions. The 1,750-ton crane has a 60-litre tank, enough for the daily consumption of its 680-horsepower engine. Climbing into the cab, I checked the RPM and steering. This mandatory inspection is required at this stage. If you finish the whole assembly and realize there's one screw left over, do you take it apart or not? The second round of testing involves the hydraulic pump mounted on the carrier. Even without the power unit and some other components installed, the hydraulic pump on the engine can still move cargo within a limited range. How do you even install the wheels on a crane that weighs over 700 tons? To be precise, each one has a net weight of 136 kilograms, and there are 18 of them on the vehicle. With a diameter of 1.5 meters and 25-inch rims, they have to use a specialized forklift for installation. In fact, each wheel costs as much as 2,500 euros, bringing the total for all 18 to at least 45,000 euros, which is roughly 368,000 yuan. It's thanks to these auxiliary machines that the two of them finished installing the tires in 2 hours. It sounds unbelievable, 2 hours to mount 18 tires. Next, we move on to the steel cable assembly stage. It is worth noting that the 700-meter cable before us is first secured manually before being wound by the machine. This winding process is extremely rigorous. They must maintain a tension of 5,000 newtons to ensure the rollers remain secure and the cable stays taut at all times. On the other side of this busy scene lies the telescopic arm production workshop. Before starting, we must first line the bottom of the inner boom with a layer of wear-resistant polyester, as this area is the most prone to wear during the telescoping process. Without this protection, the high temperatures would inevitably grind the metal down. Since the weight of each boom section on the 750-ton crane varies, take the base boom, for example, the thickest outer section, it weighs at least over 20 tons. The second and third sections that fit inside are about 8 to 16 tons, while the final, innermost section is the lightest, at only 5 to 8 tons. Whenever the telescopic boom reaches a certain position, shims must be installed, reinforced with steel plates underneath. This effectively lifts the inner wall. However, these iron casings alone are insufficient to support the boom's operation. Therefore, once it is fully secured, the engineers must proceed to install the final hydraulic system, which is what enables the original 10-meter boom to extend to several dozen meters. You can see a groove on the inner wall and a protruding pin on the side of the hydraulic cylinder. When it reaches a certain height, the inner boom locks into place, providing support. This way, no matter how long it stays there, it won't slip or fall. The telescopic crane is equipped with 4 hydraulic outriggers. Once ready, it can lift the 26-ton cab that was prepared earlier. The crane features 2 cabs, one for driving and the other for operating the telescopic boom's lifting mechanism on the cargo bed. To ensure maximum stability, the outer ring requires 88 more expansion bolts than the inner ring, for a total of 388. 2 engineers stand on either side of the turntable, tightening the bolts each time it rotates forward. Next, we install the hydraulic cylinders, 6 meters long, 50 centimeters wide, weighing 2 tons. Each weighs more than a car, not to mention the cost or its vital role in the crane. Pivot pins are inserted into the front and rear holes and secured with specialized bolts. With that said, the next heavyweight component, the telescopic boom, is ready for installation. Now its net unit weight has reached 35.7 tons and it is 16 meters long. It will take them at least 2 hours to secure it precisely in place. During the installation of the telescopic boom, it slides into position and the grease provides just the right amount of lubrication to the bushing. Therefore, the closer it gets to the end, the faster the engineer goes through the grease. The clearance between the telescopic boom and the crane is extremely tight, barely the thickness of a few sheets of A4 paper. To ensure smoother pin installation, the engineers used an orange clamp. It's no exaggeration to say it takes less than 10 seconds to install. But beyond the small pin mentioned earlier, there's a larger one below that connects to the 2-ton hydraulic cylinder. It's what controls the angle of the telescopic boom. So, how do we ensure that the current crane meets Liebherr's standards? To address this, they assign the engineers a testing task. First, they observe the slewing performance with the telescopic boom in an upright position indoors. Then, they move outdoors to a designated area to observe its lifting performance. Every crane fresh off the line is brought to a dedicated site for at least 3 days of rigorous testing. One of these, known as load testing, is the most time-consuming, often requiring several hours of continuous operation. The second phase involves testing at various speeds under normal road conditions, as well as turning and challenging lateral maneuvers. And that is how you get a €4 million crane.